Good evening. Okay. I just want to make sure it's working. Welcome to the Young Scientist Roundtable. I do want to talk about Roundtable Part 2. Looks like there is still some confusion about what Roundtable Part 2 is. Roundtable Part 2 is held immediately after the Roundtable Part 1, which is the main event, that goes from 10 after 8 for 30 minutes. That is in a classroom, and that gives a chance to the young scientists and learn more about the field. Everybody is welcome to attend that. That does go up to 8:40. I generally stop that session at 8:40, but the young scientists typically still hang around the speaker for another 10, 15, 20 minutes. But that gives an excellent chance to learn more about the field if the young scientist has some more questions and has some more information that they need to gather. So, open for all, the Young Scientist Part 2. Last time, 2 weeks ago, we had a speaker talking about the aspects of space, but that topic was space foods. She was a food scientist. Today, we are also dealing with the space, but here we have got an astrophysicist. Dr. Palma is Professor Emeritus of Physics and Astronomy at Mankato State University. He received BS in Astrophysics from Indiana University, MS and PhD in Physics and Astronomy from Rice University. He taught at Sam Houston State University in Huntsville, Texas for 24 years, of which 8 years he was chair of the Department of Physics. He came to the University of Minnesota as adjunct professor of physics and served as a senior research associate at Texas A&M as well as University of California at San Diego. He also worked at NASA's Johnson Space Center. So about his research, for 40 years, Dr. Palma used ultra-high vacuum mass spectrophotometry to measure noble gases and nitrogen in extraterrestrial materials, which include lunar samples, meteorites, interplanetary dust particles, and the material that came with NASA spacecraft missiles, spacecraft missions. He has been recognized Excellence in Research Award he received from both Sam Houston State University as well as Mankato State University. He was Distinguished Faculty Member Award. He received Distinguished Faculty Member Award at Mankato State University. He also was chosen to give Moore Lecture for his internationally recognized research. He is a member of an international team to study samples from the 2 missions, Genesis and Stardust. That brings him to today's speech. He'll be talking on NASA's Stardust Mission, bringing Comet Ville 2 to Earth. Dr. Palma.
Well, thank you very much, Vinod. It's a great honor and pleasure to be here again this evening. This is the 3rd time I've spoken to the Young Scientist Roundtable, and it's really a great program. I want to share a brief story before I get started about how I became a scientist. When I was young, I didn't know any scientists or engineers, and I really had no plans to become a scientist or engineer. And it wasn't until I was in high school and I took a class in astronomy that I got interested, and it changed my whole life. And here I am now, just newly retired. I finished in my last school year in May, and I couldn't be happier with the career path I chose. But I think of what a great opportunity all of you have of listening to scientists and engineers from all these different disciplines speak about what it is they do, why they are interested in what they do, and can share some of the passions and insights into their field. And I hope some of you get inspired by some of these speakers to seek some sort of career yourself in science or engineering. It's something that we need more and more people in all the time. Our world is becoming more technologically advanced by the minute, and we need young people who are willing to ask questions and tackle difficult problems and make a contribution to the advancement of humanity. And we need more and more of those people every year. And so I hope you will think about that as a career. So let me tell you a little bit about my project that I wanted to share with you tonight. First of all, when we talk about the solar system, this is sort of the picture that people normally see in their textbooks. They see the planets, and they have the sun there. And this picture is actually one which is not really perfectly accurate in the sense that, yes, the planets are the appropriate sizes relative to the other planets and to the sun, and they're actually spaced out more or less appropriately, but they're not at the same scale. If you make the sun the size of a silver dollar, say, something about this size, then Neptune needs to be a football field's distance away in order for it to be in the appropriate scale. And so when you think about space in the solar system, it's mostly empty space. And so this kind of a picture is not in giving you the appropriate scale exactly. But besides the sun and the planets, which are the most obvious parts of our solar system, there are other parts of the solar system as well. There are parts of the solar system which extend out beyond the planets. There's the Kuiper Belt. The Kuiper Belt is beyond the orbit of Neptune and includes where Pluto is, but there are many, many other objects out there as well. And so this part where we're not seeing anything in the middle is where the planets are, but then there's this disk of other material out there as well, which is part of our solar system. And then if we go out even further, we see that this little disk is at the center of a huge cloud of material, which is called the Oort cloud, named after an Irish astronomer, Jan Oort. And that extends out more or less to about halfway to the distance to the nearest next star beyond our sun. And so this is an enormous solar system of ours, and the planets only make up a relatively small, close-in part close to the sun. Now, a lot of these objects in this belt of material that is called the Kuiper Belt were not even known about until the 1990s. We theorized that they were there, but we didn't have telescopes good enough to actually discover them until about 1992. Now we see that there are several thousand of them which are known. Those are those little green dots that you see there. And you can see the planets are right near the center where the sun is. But those small green dots include some objects which are bigger than Pluto, which is one of the reasons why people have suggested that maybe Pluto shouldn't be considered a planet, because if we consider Pluto a planet, then what about some of these other bigger objects which are out even further? Do we call them planets too? So now they've sort of adopted a new terminology called dwarf planets, so we have a second-class status for Pluto now. But these objects out there were not even known to be there until the 1990s, so relatively recently. So let's think about this. We've got the big sun, we've got these big planets, we've got the Kuiper Belt, we've got the Oort cloud. Where does all of this come from, and how do we come up with a theory or a model which explains where we are today? And so we're trying to come up with theories which explain how the solar system formed. And so how do you do that? How do you look at the solar system today and go back in time to where we started? One of the ways is by looking at the small leftover debris of the solar system, and that's where the comets come in. So if we look at sort of a standard model of the solar system and how it formed, we start out by saying that there was this compositionally uniform cloud of material. The Greek word is nebula, and so astronomers talk about the solar nebula as being this cloud of material that the 99.9% of that material became the sun. The sun represents 99.86% of the mass of our solar system. So really, the planets and all this other stuff, we're really small potatoes compared to the sun. But that leftover material is left over in some cases from that earliest time of the solar nebula. And so if we study it, we can get a picture of what the material was like that the sun and planets formed out of. So here's a picture of that solar nebula about 4.6 billion years ago. And you get an idea of it and its size. It's sort of a pancake shape, although there are jets of material perpendicular to the plane of the pancake. And you see way out there on the edges is this Kuiper Belt of material, which still exists. And that's the source of short-term comets. And that's what we're going to be talking about today. The solar system contains billions of comets. And they're wonderful objects to look at. So if you ever get the opportunity, there's something in the newspaper, say, about a comet being a really pretty one to go out and see, you should try driving outside of the city where it's nice and dark and looking up, and you can see some of these marvelous phenomenon in the sky. So these three pictures are pictures of comets from the Earth. And of course, usually they try to put some sort of other object in the picture to give it scale. So you see a saguaro cactus on one side and a palm tree on another, and Big Bend in the middle. But these are spectacular phenomena to see. These are pictures of comets as they appear from the Earth. So what about what they look like when they're out in space? Well, it wasn't until relatively recently that we actually had the capability of doing that, of actually seeing what a comet was like close up. And the first opportunity to do that was to see the comet Halley. So how many of you, let's see a show of hands, saw Comet Halley back in 1986 when it came around? Of course, you have to be a little bit older than most of the students here in order to see that. Well, that's great. It actually turned out not to be one of the better apparitions, as they say, of Comet Halley. It was better in 1910, but I won't ask if anybody was around to see it then. But for the young people in this audience, you'll get a chance to see Comet Halley in 76 years after 1986, so you can do the mathematics there, and you'll see that it's about the year 2062, okay? Comet Halley tends to be something which people see once, and that's it. But if you notice, this is a picture of the nucleus of Comet Halley taken from the European Space Agency's Giotto spacecraft. Now I want you to notice, as we go through the next couple pictures, how much that space photography has improved. This is 1986. Well, the next one that we're looking at is from a NASA mission called Deep Space One, and this is now 15 years later, and they took a picture of Comet Borrelly. And here you see Comet Borrelly, and the picture's a little clearer and a little sharper and a little better than the previous one. You see jets of gas there coming off of the comet. It's glowing, which is what causes the comet to have its tail, right? And so this is Comet Borrelly. Now look at this picture. This is a picture from the Rosetta Mission, 2015. So just a few years ago, the European Space Agency had a spectacularly successful mission called the Rosetta Mission, which visited Gerasimenko, and I'm sure anybody who has any Ukrainian heritage is cringing in their seat. But anyway, this is an incredible photograph of this comet close up, and you can see it has a very unusual shape. So why are comets so important to understanding the solar system and how it formed? It's because they're primitive. And what do we mean by being primitive? It means that they have had very little heating or very little water changing them. And so they tend to be objects which come from far away from the sun, and so they haven't changed much. It's like they've been in a deep freeze for the last 4 billion years or so. And so they are preserving the clues of how the solar system began within them. Some of them actually contain material that's older than the solar system itself, which is pretty amazing. So let me tell you a little bit about this mission tonight, which is the Stardust Mission. The Stardust Mission was one of the NASA Discovery Program missions, of which there have been a number. Here are 12 of them, and there are more of them happening all the time, so I'm not sure I have all of them. I think I do. But they are missions which are smaller in scope and are really driven by science. They're designed by scientists, they're driven by scientists, they try to do the missions in a shorter period of time and get results quickly, okay? These missions cost, they used to have a limit of about $300 million, which sounds like a lot of money, but when you start talking about some of the big missions where they go around Jupiter and Saturn and all those missions cost well over $1 billion apiece. And the problem with that is, if you put all your eggs in one basket and that basket breaks, you've lost a lot of money. So the idea of these Discovery Program missions was to do missions which were smaller in scope and really driven by the science. And so you can see there are 2 missions there that are underlined and in bold, and those are 2 missions which I have been part of. And they're both sample return missions, and they're the only 2 missions up there that are sample return missions. So what does that mean, to have a sample return mission? It means it's a mission that went out into space, took a sample, and brought it back to the Earth for analysis. Why is that important? Well, because you can do a lot here on the Earth that you can't do in space. There are a lot of advantages to having a sample in your laboratory than trying to do an analysis in space. And so I've listed a whole lot of different things here, and I won't read them all off to you, but I will highlight 1 or 2 of them that I think are particularly important. And one of them is this one near the end. The analysis is not limited to pre-flight ideas. If you think about it, a mission has to be designed to do something in particular. Better to bring samples back where you can discover whatever they have to offer. And so that's why, of course, I'm an experimental scientist, so I would be partial to this kind of a mission, right? But these are missions that brought samples back to the Earth for analysis by scientists such as myself in laboratories. And there are lots of big advantages. So let's talk about this Stardust mission. The Stardust mission traveled out to the comet Ville 2. It looks like Wild 2, but it has nothing to do with our hockey team. It's actually pronounced Vilt 2, like a V-I-L-T, because it's not an English name, Ville 2. And it returned those samples to the Earth for analysis. And the idea was, let's take this piece of a comet and compare it to the samples that we have from meteorites and from asteroids and from lunar samples and see what's different about these and what can they tell us about the history of the solar system. So here's this comet Ville 2's orbit. The thing that made Comet Ville 2 so desirable to go see was that for most of the history of the solar system, it was way out there in the Kuiper Belt, far away from the sun, and so it was in the deep freeze, not being changed at all from the very time that the solar system formed. But slowly it came in towards the inner part of the solar system, which comets by their nature do, and it suffered a fate that many objects do when they come in closer to the sun. It went by the planet Jupiter. Jupiter, being the biggest planet, exerts a big gravitational force on small objects that come anywhere near it. And so what happened was it changed from that yellow elongated orbit into that little red orbit, which is close to the orbit of the Earth. So we've changed from this orbit into this orbit. And that's all because of the influence of Jupiter. Ville 2 came close enough to Jupiter that it changed its orbit and made it so that it went close to the Earth. Now, that's important because we don't have the capability of sending a spacecraft way out into the deep part of the solar system and back with a sample. That would take way too long and it'd be very, very difficult. But now the comet has come close to us. And not only that, the comet did this in just 1974. So that means that the comet is really fresh. It's been in the deep freeze until very recently. And so now it's coming around close to us, and it has not been around the sun very long. So it hasn't changed. If you think about old comets like Halley's Comet, that comet has gone around the sun many, many times over its thousands of years that it's been in its orbit. And so it's changed tremendously. But this comet has not. So it still contains all those pristine records that we want to study. Here's the spacecraft while it's still getting prepared for its mission. That's the sample return capsule, and we'll see that more later. These are the solar panels which provide the energy. And then these are little bumpers which are actually there to protect the spacecraft from some of the particles coming off the comet, and we'll see that later. This is what collected the particles from this comet. It's a collector which kind of looks like a large ice cube tray, although I'm sure all of the kids in this audience have no idea what an ice cube tray is. But back in the olden days, when I was your age, they had these trays that you filled up with water to make ice. The refrigerator didn't do it for you automatically. So anyway, that's about what the size of these things are. What's inside there to collect the sample? It's this very special, unusual material called aerogel. Aerogel is incredibly low density. The density of it is only a little over twice the density of air, but it's a solid material. So it is the least dense material that you can make into a solid. And I actually have a little sample of it that I brought with me, so you can come up afterward and take a look at it. It looks like it would be very spongy, but it's actually a glass. It's actually very brittle. It's a very low density glass. And that's what the material is that collected the particles from the sun, from the comet, sorry. So why is it made out of that? Because what happens is the particles coming from the comet are moving at very high speed. If you try to stop them quickly, they're just going to splatter all over. You want to collect them and slow them down slowly so that they remain intact as much as possible so that you don't change what it is that you're actually capturing. And that's why we have this very low density material called aerogel. So let's look at what happened with the mission. The mission was a long mission. It actually was launched in February of 1999 and didn't come back until almost 7 years later. So it was a very long mission. And it went around on 3 big loops around the sun. And on the 3rd loop, it encountered the comet Ville 2. Now you think about how difficult this must be to figure out. They had to figure out how this was going to travel for 7 years, and in the process, it was going to be encountering a comet which is zooming by. It's like trying to fire 2 guns at right angles and have the bullets pass right by one another. It is an extraordinary engineering feat and calculation feat to come up with this process and this orbit and have it all work. One of the things that the mission did, or the spacecraft did while it was in its orbit, is it went by an asteroid, and the asteroid had the name Anne Frank. People who discover asteroids get to name them whatever they want, and so someone who discovered this asteroid named it Anne Frank, and so as it traveled by, it took this picture. It's not a particularly sharp image because it wasn't that close to it, but this is just a little side light of the mission. So let's see what this looks like. Here it is. This is obviously an artist rendition. We didn't have anybody out there in space taking a picture of the spacecraft as it encountered Comet Ville 2. But now you have an idea of what this looks like. Okay? You see the solar panels are all laid out there, and you see those bumpers on the front which are protecting the solar panels and the spacecraft from the impacts of these particles. And meanwhile, we have this thing sticking up there, which is what's collecting the particles. That sample collector is about the size of a large tennis racket, okay? And the head of the tennis racket, after it finished collecting the particles, folded down against the arm there that you see sticking up, and then the arm folded down into the spacecraft sample return capsule, and then the lid of the capsule closed, and then it was jettisoned out, and it came back to the Earth. Okay? So, quite a complicated mission. Here we are at Comet Ville 2, and you can see what the comet looked like before it started creating this big tail and all. And most of the features on it change because of the fact that it's losing material all the time. But you can see there's a left foot and a right foot. Left foot, right foot. And these other features are named after scientists. So you too can have a feature on a comet named after you if you become a scientist. Of course, because the comet goes around, it changes all the time. It may not be there the next time it comes around, but oh well, you know, fame is fleeting, as they say. So here's the sample return capsule when it came back 7 years after. See it there in the clean room in the Utah desert next to several scientists. And so you can see it was not a large sample return capsule. So here's this particle collector before it went off into space. Looks very nice and pristine. There's 132 rectangles in there collecting material. This is what it looked like afterward in terms of a schematic showing where particles hit the sample return collector, okay? And so there are some blue triangles which represent where particles hit the aerogel material, and then there are some red dots which is where particles hit the frame around the aerogel and created craters, because that frame is also a collector of material. So here's two impact sites close up. These are big impact sites. Here and here. And here's a close-up of one of those. So you can get an idea of what happens when a particle hits at about 6 kilometers per second. It's moving at high speed. So what happens? Well, here's what people see when you shoot materials at a high speed into aerogel. You get this carrot-shaped track, and then at the end is the particle. So you always can find the particle that made the track. All you have to do is follow the arrow down to the end, and there's the particle. Okay? And meanwhile, the aerogel has slowed the material down so it doesn't hit at too high of a speed. Well, here are the particle tracks that actually were in the aerogel, not the ones in the experiments. They don't look very similar, do they? Let's go back. There's the experimental track. Here's the actual thing. What happened? Well, when you have this situation, they're firing things like little BBs. I mean, not literally BBs because that's too big, but something which is very solid and stays in one piece. But if you take a piece from a comet is made up of little pieces of material that are stuck together, and when it hits, it fragments. And when it fragments, it sends material out and causes this big bulge. But still, there are little pieces all along there in this material, and those are the materials that are from the comet. So, what's my research? Well, what I do is I study the noble gases and nitrogen in primitive solar system materials. Why? Because, again, they are tracers of processes in the early solar system. And how do you do this? I do it by what's called high sensitivity mass spectrometry. So here's what my laboratory at the University of Minnesota looked like. I say looked like because it's no longer in existence. When I retired, the lab got cannibalized, so it's no longer there. But that's what it looks like. Most laboratories are sort of messy, and mine was no exception. So what happens with these samples? We take little tiny samples, and we put them in platinum foil, and then we run an electrical current through the platinum foil, just like an old-timey light bulb, an incandescent light bulb where you have a glowing filament. Well, just imagine the filament having a little tiny sample on it, and then it heats up the sample, and when it heats up the sample, it releases gases, which then I can analyze, and that tells me something about the sample. And so that's what the process is. So those of you who don't remember your chemistry, or maybe it's been a few years, the noble gases are the ones on the far right. The ones that are stable are the ones in the red box there: helium, neon, argon, krypton, and xenon. Why are they important? They're interesting and important because they are inert. They're noble gases. They do not interact chemically, and so they turn out to be excellent tracers of processes that go on in the early solar system. So just as an example, let's look at the lightest of these, helium. Helium has 2 isotopes. So of course you know there are elements which are determined by the number of protons, but each element can have more than 1 isotope, which is dependent upon the number of neutrons in its nucleus. So helium has helium-3 and helium-4. Helium-3 has 2 protons and 1 neutron. Helium-4 has 2 protons and 2 neutrons. And by looking at the relative amounts of these 2 isotopes, and in the case of neon, 3 isotopes, in the case of argon, 3 isotopes, in the case of krypton, 5 isotopes, in the case of xenon, 9 isotopes, you can tell something about the actual samples. Okay? So, how does mass spectrometry work? A mass spectrometer works by taking sample gas, ionizing it, which means making it charged, and then sending it through an electromagnet. And by its motion through an electromagnet causes it to bend, and then you analyze the different constituents or parts of the gas individually. Mass spectrometers are used in every area of science that you can think of. Every one. There are hundreds of different kinds of mass spectrometers. And mine was just a specialized one for the kind of samples and work that I do. So these noble gas concentrations and isotopic compositions tell me information about the early solar system and may actually tell me something about interplanetary dust particles, which are another kind of interplanetary sample that I study. So let's look at some of these samples, and I can go through these pretty quickly. These are some of the samples that came back from the Stardust mission. You can see just how small these samples are. This scale bar is 1/2 millimeter, and this is the track. So the particle came in, hit here, and then there are particles all along here, all around here. So there's particles in the aerogel that we're analyzing. There you can see the track in the whole aerogel sample. So what we did is we took samples out of the aerogel. This is one of those ice cube tray pieces. We cut them out, and then we look at different parts of the sample track. So for example, here are various little pieces of this track which was created by a particle from the comet. And so by looking at those, we're trapping within the aerogel little pieces of the comet. Not only that, we have samples which we take from the surface of the aerogel because very, very fine dust did not penetrate like those big particles. It just settled on the surface. And so we analyzed the surface as well. So just to give you an idea of another surface, here's a surface of another cell that we looked at. And if you look at the surface, you don't see anything inside this red circle. But if you focus slightly below the surface, you find that there are little particles. And so some of the particles are ones that you can't actually isolate by themselves. You have to take the aerogel with them, and the aerogel doesn't have any noble gases, so you just analyze the sample which is within the aerogel itself. Here's an example where we actually analyze the individual particles. This is the track, looking at it sideways, and each of these little things that's in little circles is a sample. But these are tiny, tiny samples. These are on the order of microns in size, so they're very, very small. Isolating them and taking them out and measuring them is a very difficult process. Here they are actually before we analyze them, and you can see the particles, when they come in, they act like a snowplow, and they push aerogel in front of them. And so this is aerogel, which is in front of this particle here. And this is a scale bar of 30 microns. So these are particles that are only about 10 microns in size, very, very small. Some particles came from those craters, the objects that hit the frame of the spacecraft. Those actually left small amounts of residue, and in one of those, they actually found a small grain, which is a pre-solar grain. A pre-solar grain means it actually predates the formation of the solar system. And you might say, well, wait a minute, how do you know that? Because if you look at its isotopic composition, the isotopic composition is so extremely unusual, it points to a formation of the sample outside of the solar system, probably in an exploding star. So what did we expect when we went to Comet Ville 2? People expected, hey, this is a comet, it was way out in the solar system, we should expect things to be non-crystalline, that is, not heated very much. They should be lots of unusual things that formed around other stars. There should be all sorts of submicron grains with organic material, all sorts of interesting things. It turns out all of those were indeed seen, but not nearly as many as were expected. And so this comes back to the importance of bringing samples back to the Earth, because what we actually discovered is very different from what we expected. What we mostly found were crystalline materials which had been heated to high temperatures, and lots of metal and sulfur and various things which were not expected. So the question is, why were our expectations and what we actually discovered so different? Well, I don't expect you to really pay a whole lot of attention to everything on this slide, but what we now know is that the solar system's formation is distinctly different than what we thought. There is a lot more turbulence and mixing up of materials rather than just having a big cloud of dust and gas which slowly coalesce down into forming the sun at the center and the various planets without much mixing. Instead, we find that there's lots of mixing. So things that get heated close to the sun and have a high temperature can get thrown way out into the outer parts of the solar system where they might become part of a comet. And so Comet Ville 2 has overthrown most of what we thought we knew about the formation of the solar system. And it has led to all sorts of new theories for how to interpret the data. And so I just throw up a couple things here from a couple recent astronomy textbooks just to show you that it's possible to have new material enter into a textbook almost immediately and change the conclusions of what we thought we knew. And so if you look at these two different quotes, they're basically both saying, hey, we have a lot different picture than what we thought we had for how the solar system began. We have high temperature materials which had to be close to the sun somehow get into things which are formed way out in the outer parts of the solar system. That means that the solar system's formation has to be one which is a much more turbulent and mixing model than what we thought. So, let me give you a few conclusions. First of all, the Stardust samples are a tremendous resource for scientists. And we've only looked at a relatively small portion of the total amount of material which has been returned to the Earth. Some of the materials even predate the solar system. These have provided the theories for the formation of the solar system. And what we know now is that some of these samples contain gases and materials which formed close to the forming sun. And the great thing about science is that questions are always changing and techniques are always getting better. So if any of you scientists decide to go into the field of solar system research, there's plenty more to do and plenty better equipment. When I first started, I had strip chart recorders that with a pen that used to measure, and I would use a ruler to figure out how much of a material I had. And when I retired, we had computer programs that did everything and made life much simpler, much more accurate. It just shows that within a relatively short time, you can change the whole basis for how you look at samples. Samples used to be great big objects that you had to look at. Now we have samples that are microns in size. I want to end by saying two quick other things. First is, if any of you get the National Geographic, there's a nice article from July of 2013. I actually brought a copy of it with me, which is a nice summary of the current thinking on solar system origin. It's about, it's 5 years old now, so it's a little dated, but most of it is actually quite accurate. It brings up a lot about the Stardust research that I was just telling you about. And so I encourage you, if you have an interest and would like to get a good layman's summary, to look at it. The other thing I wanted to say is there are other sample return missions which you'll be hearing about in the newspaper. They might even be accurate stories, who knows? But two of the missions have been by the Japanese. The Japanese have two spacecraft called Hayabusa 1 and Hayabusa 2. They went to various asteroids and are returning samples. One returned a sample in 2010, the other one's coming back in 2020. NASA also has an asteroid return mission, which is called Osiris-Rex, and it's visiting an asteroid called Bennu, and it will be returning samples in March of 2021. Unfortunately, I won't be analyzing any of these samples now that I'm retired, so one of you is going to have to step up to the plate. Thank you very much.
Thank you, Dr. Palma. If you have got questions, raise your hands. Preferences for the young scientists.
Yes.
Oh, yeah. Well, how come you don't use radon and oganesson?
Oh, very good. Wow. Okay, somebody that knows the last two of the noble gases. Both of those are not stable gases, okay? And so radioactive gases are not ones that most scientists want to deal with if they can avoid it. There's another thing, though, and that is as elements get heavier, they generally become less and less, there's less and less of them. Okay, and so the last one is one which they have seen, I was just looking that up today as a matter of fact, they think that there have been 5 or 6 atoms detected of oganesson. 5 or 6 atoms, that's total, right, in the history of mankind. So we're not going to be looking for that in any comets. Radon also is one which, even if it's there, which it might be, it would be in such low abundance, it would be extraordinarily difficult to find and measure. So we try to look for things for which we have enough signals that we can actually make a measurement. And so it gets harder as you get heavier, and that's the main reason. Uh-huh.
Why did you want to send a comet to Earth?
I'm sorry, I didn't quite catch that.
Why did Why did you want to send a comet to Earth?
Oh, why did we want to send a comet to Earth? Okay, again, the reason we want to bring a comet to Earth is because we're studying how the solar system formed. And we think of comets as representing material from the time that the solar system formed. And so, if you want to know how you get to today, you have to know how you started. And that's not very easy. For example, suppose you want to know the history of the Earth, and you go out to your driveway and you pick up a rock out of your driveway. That rock has gone through so many changes from the time that the Earth first formed that it's not going to tell you very much about the initial material that the Earth formed out of. So we have to find samples that are pristine, which are not altered by all sorts of different processes. And comets are one of the ones that fill the bill for that. Thank you for your question.
Okay, go ahead.
How long will Comet Ville be around?
That's a good question. Comets lose material every time they go around the sun. That's how they form that big tail, right? That's material from the comet, which is being blown off of it. How many of you have ever gone out to see a shower of meteors? Many of you? Okay. Shower meteors are from comets that broke up. So when a comet goes around the sun, each time it loses material, and it loses more material, and it loses more material, and eventually it tends to break apart. And then it forms a whole bunch of little pieces that spread out all along the orbit. And then when the Earth goes through that path, those little pieces of the broken up comet come into the Earth's atmosphere and form shower meteors. And that's why they always appear to be coming from the same direction in space for a particular shower of meteors. It's because that's the direction of the old orbit of the broken up comet. So to get back to your question, we don't really know for sure how long Comet Ville 2 will be around. Most comets about the size of Ville 2 are about 5 miles or so in diameter. They probably will be able to go around many, many times before they break apart. But then every now and then, they interact with something like Jupiter, and it causes them to fragment. So I can't answer that question completely. That's a good question, though.
How did the NASA Discovery program name the missions? Like some of them sound like Greek or Latin.
Okay, I think I heard that you wanted to know how they got the names. Yeah, so NASA loves acronyms, okay? They have an acronym for everything. So typically what they do is they try to come up with some sort of an acronym which then describes the mission. Now, the Stardust Mission, they just used Stardust, and the Genesis Mission, it just is Genesis. But for example, if you look like at Grail or Insight or some of these other ones, they're actually an acronym for a whole bunch of things, and they have, some of them are quite tortured actually, but they come up with something that sounds cool, okay? But the Stardust Mission and the Genesis Mission, the two that I was most involved in, those missions, the names, I don't know exactly how they came up. Some of them have had contests and all where they ask for suggestions. But also some cases they have the scientist who is the principal investigator is the one who comes up with the name. Each mission has one principal investigator who is really the head honcho for all of the scientists. So I was part of the mission team for Stardust and for Genesis, but there were dozens of scientists in that team, and only one guy who was the head guy. And the person who was the head person for Stardust was a man by the name of Don Brownlee, a scientist from the University of Washington, and he may be the one who actually came up with that name. But if you look at some of the other names, you'll see that they're just acronyms for something else.
I have two questions.
Okay.
How fragile are comets, and how big are usually the debris that comes down to Earth?
Okay. So, how fragile are comets? Comets typically are very loose assemblages. They're not really like a rock that you would get out of your driveway, okay? The density of material tends to be pretty low, so 2 or 3 grams per centimeter cubed, which is, I don't really want to throw numbers out there at you, but basically they're fairly crumbly. They're loose assemblages of material, all right? Now, whether or not there's actually cometary dust that has made it down to the Earth is something that we're not absolutely 100% sure of. It almost has to have happened. We have material called interplanetary dust, which is dust which is out there in space, and it comes into the Earth all the time. All the time. And so that's actually another class of material that I've studied. And some of that comes from asteroids, and some of it comes from comets. But one of the key things that we're not 100% sure of is which dust comes from comets and which dust comes from asteroids. And that's actually one of the key things that this Stardust mission was supposed to help us decide. Because now, with this sample from Ville 2, we have the first material that is unequivocally from a comet. This is the first material that is unarguably from a comet. There were all of these other materials that people have analyzed, and people have made arguments that said, oh, this must be cometary for this reason or that reason, but nobody could say for sure. But this sample we know came from a comet. So now the question is, if I study this material and I analyze it, can I come up with markers which will tell me which of these other samples also come from comets? And we're still working on that. And actually, I'm just in the process of publishing a paper in the next month, which has to do with this question. So, good question.
Yep.
If one of those little ice tray cubes of the aerogel material were to be full, how much would it weigh?
Okay. I think I missed the first part of the question. What was it, the first part? How much would a big sample of it weigh, or?
How much would if one of the cubes?
Oh, okay, one of the cubes. Well, you can figure it out by knowing that the density is so low, and then figuring out how big one of those cubes is. Those cubes are roughly 2 centimeters by 4 centimeters by 4 centimeters. So you can figure out the volume there and then multiply that by the density, which is 0.001 or so grams per centimeter cubed, and you'll come up with a darn small amount of weight, okay? This material weighs practically nothing. It's extraordinarily light. And so I invite you, as I said, to come up and take a look at the sample that I brought with me. It weighs practically nothing. So 0 would be a good answer, I guess.
We will have to close this session as it is 8 o'clock, but I do hope that many of you can join in 10 minutes for the round 2. The next Young Scientist Roundtable, December 12, Dr. Stein from Boston Scientific. He's the Chief Medical Officer at their Cardiac Rhythm Management Research Area. That is going to be another wonderful presentation in the biological sciences. I hope that you see that. I hope you are able to come and attend that marvelous presentation from Dr. Stein. But here, let us first acknowledge for a wonderful service that Dr. Palma has provided for the Young Scientist Roundtable this evening. Thank you, Dr. Palma. Appreciate it.
Thank you very much.
I was trying to get Dr. Palma for 2 years, and you know why.
Oh, you want to see the sample? Yeah. Yeah, let me put this down so I don't break it.